More, wasn't it?
No, it's for Anthony.
Yeah. So a BTU is the amount of heat required to raise the temperature of 1 pound of water by 1 degree Fahrenheit. That is a definition of a BTU. Now, I just told you if I had 1 cubic foot of natural gas, I can get 1,000 BTUs out of it. So what this is called, this 1,000 BTUs per cubic foot is called a heating value. And sometimes they call this heating value also calorific value. It's the amount of heat energy per a certain volume of gas. Okay, that's really what it is. Now, there is another one that we need to be concerned about, and that is C3H8. And this is propane. And propane also has a heating value. So if I had 1 cubic foot box, so 1 cubic foot of propane gas, this is gas only, not a liquid yet. This is just C3H8 propane gas. You can get 2,500 BTUs per cubic foot. So the heating value of propane gas would be classified as 2,500 BTUs per cubic foot. So those are a couple of things that you need to know. These are 100% need to know. I'm going to also put in butane here. And butane has a chemical symbol of C4H10. So that's the chemical symbol for this hydrocarbon. So there is commercial isobutane, and there's also butane that we carry in our pockets a lot, right? It has a heating value, so 1 cubic foot of butane has a heating value of 3,200 BTUs per cubic foot. So those are 3 heating values that you need to know. Now let's talk a little bit about air. Does anybody know how much oxygen there is in air? Anybody?
Isn't it like
79%?
Because I know it's 80% nitrogen and then it's like 19% oxygen and then like 1% miscellaneous.
Sure. So it's about 20% oxygen, O2. It's about 79% nitrogen. By the letter N. Let me just write oxygen here. Oxygen. And we write that as O2. And 1% other gases. And those other gases are carbon dioxide mostly and other things. So this is what air is made up of. Now, as you know, in our combustion triangle, we need air for combustion. Yes? So we are going to talk about well, if I can spell, theoretical air. And theoretical air constitutes primary and secondary. Oh, secondary air. So that is theoretical air. So theoretically, we need a certain amount of air for the ability to combust natural gas. So if natural gas is 1 cubic foot of CH4, so 1 cubic foot of natural gas requires 10 cubic feet of theoretical air. So for every 1 cubic foot of natural gas that you burn, you need 10 cubic feet of air. Danica, looks like somebody wants to help you with your schoolwork here.
She's trying.
Was it just holding the pencil there a second
Yes.
ago?
Yes, she was.
Fantastic. That's awesome. Okay, so 1 cubic foot of CH4 requires 10 cubic feet of theoretical air. And we're going to take a break here in a second, but I'm just going to give you the theoretical air amounts for each of those 3 gases. So C3, why does that keep doing that? C3H8 propane gas. I want to make sure that we're talking about gas. Requires, so 1 cubic foot of propane gas requires 24 cubic feet of theoretical air. And 1 cubic foot of C4H10, which is butane, as a gas, not as a liquid, requires 30 cubic feet of theoretical air to burn. Theoretically, this is theoretical air. So write that down, let that sink in. Let's take a 10-minute break. We'll come back at 9 o'clock and we'll continue on with a little more of this.
Hey, Doug, I got a quick question.
Sure.
Me and Kyle, we were talking when we were at work together that natural gas actually doesn't need air to explode. We were talking about that, and if you get natural gas hot enough, I believe was the conversation, that it would literally just combust on its own.
Nope. It needs air. If you don't have parts of the fire triangle, you're not going to get combustion. In the middle of a natural gas cloud, you could light a cigarette if you have enough air. You won't get that gas combusting until you have the right mixture. Okay?
All right.
And we're going to talk about that when we go through properties of gases and what that mixture actually is.
Is that the lower and upper explosive limits?
That is exactly correct. Whoever said that. Okay, so let's take a break. 10 minutes. Go for a walk or get some more coffee or some more liquids, Matt. Okay? All right. Here we go. I'm going to share my screen again. Okay, so we just talked about what theoretical air is. This is theoretical. So hold on to that thought for a moment, because I want to talk a little bit about what this is. Input. Input values are what is typically given an appliance. An appliance will, on the rating plate, will have an input value. And I think in previous years, you learned how to get efficiency, where we have output, input, and percent efficiency on any appliance. No appliance is 100% efficient. It's impossible. And we're going to talk about categories of appliances coming up in the weeks. And for the most part, we are going to talk about category 1 appliances. Okay, that for the most part, we're going to talk about category 1 appliances. And this is where appliances are buoyancy vented, meaning they have a vent tied to the outdoors and through difference in air densities that makes the motive force inside a vent take away the products of combustion. Okay, and that's part of what we have to do. So inputs and outputs would equal percent efficiency. I don't even know how to spell efficiency, but that is not right. It doesn't look right. So don't listen. I'm a plumber, gas fitter. I'm not a brain surgeon. So I may get a couple of spelling errors as we move on. So I want to ask you, so since we know what heating value is, if I had an appliance that has 100,000, thank you very much for that, Tozel. See how good this works now? See how good that works? That's amazing. If I had an appliance that was 100,000 BTUs per hour and it was burning CH4, I am going to ask you a question. How many cubic feet of gas is this?
That's 1,000 cubic feet.
That's right. So we can do another formula triangle where we can put an input. Oh, I even spelled that wrong. An input, or I should actually rephrase that. I could put a BTU value and I could divide it by the heating value, and that will give me my cubic feet of gas. Yes? Okay, so how about that 100,000 BTU appliance? BTUs per hour, because most appliances are rated in BTUs per hour. It'll tell you how many BTUs they burn in a period of time. And that time is usually in hours. And if it was burning C3H8, how many cubic feet of gas is that?
40?
40 cubic feet. So what you did there is you took 100,000 BTUs per hour and you divided it by 2,500, excuse me, 2,500 BTUs per cubic foot, right? That's the heating value, and you will get your cubic feet of 40. Correct. That's pretty good. Pretty easy stuff. Now, what we also do is we shorten the 100,000 and we call it MBH. And that is 100,000 BTUs per hour. The M here indicates 1,000. So anytime you see this kind of thing, 100 M MBH, it is equal to 100,000 BTUs per hour. Okay, so that's just a shortening. It's almost like a modified geodetic. You know how we have a geodetic elevation and then we modify it? This is basically what we're doing in this regard. Okay, is when I have 100,000 MBH, it equals 100,000 BTUs per hour. Stop me anytime if you have any questions on this. So now, for example, if I had an appliance that has 1,000 MBH input, how many cubic feet of C3H8 is this?
400.
So you took 100, or you took 1,000,000 divided by 2,500. So this is 1,000,000 BTUs per hour, and you divide it by 2,500 BTUs per cubic foot, and you came up with 400 cubic feet per hour. Okay, you can see how we want to carry through the increments of measure. The BTUs get canceled out. I'm left with cubic feet per hour still. So this is how much gas we will be burning in 1 hour of time. Now I'm going to take this a step further. That efficiency thing keeps following me around. Toslin, you got to delete that on there. Thank you. So I'm going to say I am burning CH4. And I have an appliance that is 36,000 BTUs per hour. Okay, that's my input. I'm going to say that I want to know how many, let me go back here a second. I want to know how many cubic feet of CH4 that is, and I want to know how much Theo air. So I want to know two things. I have 36,000 BTUs per hour input. How many cubic feet of natural gas is that? And how much Theo air do I require?
36 cubic feet of natural gas and 360 cubic feet of theoretical air.
So I have 36 cubic feet of CH4, and I know that I need 10 cubic feet for every 1 cubic foot of natural gas. So that's Theo air. So my Theo air is 360 cubic feet per hour of theoretical air. That's an enormous amount of air required for that appliance for 1 hour. And that would be simply 36,000 BTUs per hour would be a simple hot water tank. That would be the amount of theoretical air required to burn this gas. Now, having said that, let's do another question. So say I have an appliance that was 125 MBH and it's burning C3H8. I want to know how many cubic feet of gas, and I want to know the amount of Theo air for this appliance.
Is it 50 cubic feet and
Yeah, I think you're right.
1200 theoretical air.
So that is 50 cubic feet of propane per hour. And then we times that by 2400, right? Or 24. For every 1 cubic foot of propane, we need 24 cubic feet of theoretical air for propane. Remember that? So that should be 1200 cubic feet theo air. Does everybody concur with that statement? Thank you.
Did you just 125,000?
That is 125,000. That is correct. So the math would look like this: 125,000 BTUs per hour, and I would divide it by 2,500 BTUs per cubic foot, and I would get that answer right there, 50. And then we take our 50 cubic feet per hour of gas and we multiply that by 24 cubic feet per cubic foot, and then I get my air of 1,200 cubic feet of theo air per hour. Yeah, perfect. Okay, you guys are doing good so far. So the next thing, so we talked about theo-air, theoretical, and we know what we need for theoretical air. So CH4, it's 1 cubic foot gas. We need 10 cubic feet theo-air. Now, this is theoretical. We need a little bit more. And we need something called excess air. We need a little bit more of the theoretical in excess, and we calculate excess air at 40% of theo air. And when you add theoretical air, so let me write over here. So we get theoretical air, and when we add excess air, we will get total combustion air. TCA, total combustion air. So excess is 40% of theo. So let me do a little bit of math around this. So if I had 1 cubic foot, of CH4, I will need 10 cubic feet of theo air. And then I need 40% of that. So 10 cubic feet times 0.4, which is 40%, will give me 4 cubic feet excess air. So I will need 4 cubic feet of excess air, giving me 14 cubic feet of total combustion air. So we add these two together to get total combustion air required to burn 1 cubic foot of natural gas needs 14 cubic feet of air. It's an enormous amount of air movement through appliances. And this is why air supply is so important to get right. Because if we don't get our air supply into the appliance correct, we will have the appliance firing incorrectly. you will get all kinds of problems. And the worst scenario out of an appliance not firing properly is people die, okay, when an appliance does not work properly, because you're burning gases, etc., and you're causing all kinds of problems. Yeah, the worst case scenario is people die. And tell you what, people die every year from appliances not working properly. Okay, so this is important for us. It's hugely important. So let's do another couple of these. So, for example, I have 250 MBH of CH4. I want to know the amount of gas in cubic feet. I want to know the amount of Theo air in cubic feet. Oh, I should... and I want to know the excess air in cubic feet. And I want to know the total combustion air in cubic feet. So get those three things from this appliance right here. Give you a second to do that.
Do you want what I?
What's that?
Do you want me to give you the answer, or should we wait?
Well, listen. What is your gas in cubic feet?
250.
250 cubic feet per hour in your gas. Correct. How about your theoretical air?
I got 2,500.
That is also correct. 2,500 cubic feet per hour in theo air. How about excess air?
1,000.
1,000 cubic feet per hour in air of excess of theoretical. And what is my total combustion air?
3,500.
3,500 cubic feet per hour total combustion air. This kind of gives us a little bit how much air is required to burn this amount of gas. So that is a very large quantity of air. If you think that 1 cubic foot box, so that's 1 foot by 1 foot by 1 foot, that's a cubic foot. You need 3,500 of these just to burn that much gas in 1 hour. So you can imagine the amount of airflow going through these appliances. And that's what I'm trying to get at. I'm trying to get at that we need an incredible amount of air for these appliances. Let's do a couple more examples. Let's see over here. Oh gosh. Okay, I need, let's say I have an appliance that has 150,000 BTU per hour input. This appliance is burning C3H8. I want to know cubic feet of gas. I want to know cubic feet of theo air. I want cubic feet of excess. And I want total combustion air.
Do you want the answer?
Okay, sure. Toslin.
60 cubic feet of gas.
Okay, let me write that.
1,000.
Hang on, let me write it down. 60 cubic feet
Sorry.
of gas per hour. Yeah. What's your Theo air?
1,440 cubic feet of air per hour.
That's theoretical air. And that's per hour, yeah. And excess?
576 cubic feet per hour excess air.
Right. Total combustion?
2,016 cubic feet of air per hour.
Total combustion air. Wow. Okay. So that's pretty good. You guys are doing quite well. I'm going to stop sharing here for a second. So what I'm going to do is in your air supply and venting course, I have just released a combustion air exercise. Now I want you to take the next hour, well, it's not going to take you that long, but it's probably to the top of the hour, till 10 o'clock. But what I'm going to do is I'm going to put you into breakout rooms and you could do them together. Okay, so you'll have somebody to bounce these numbers off. Take your time. You have lots of time to do it. So this is called the combustion air exercise. It is in your air supply D2L shell, and you will see it there. So I'm just going to randomly put you guys in breakout rooms, and we will do that. So I'm going to do 6 rooms, 3 to 4 participants per room. Good luck. And go. Thank you. Let me share my screen here. Is everybody familiar with that picture? That should be pretty familiar, right? It's a little hot water tank, yes? Okay, so in this scenario, if I had my gas line, and the gas line connects down here. So if I was draw an arrow, it connects to the gas valve right here. Everybody see where my little pen is? That's where the gas line connects to, right? That is the gas control valve, or they call it here temperature control. We're going to talk about that control and how it works later on. But what I want to get to you, if I put a gas line in here, so there's my gas line, and I put in 1 cubic foot of gas in there, okay? 1 cubic foot of gas into this hot water tank. So underneath that hot water tank is the burner, and there's the flames that would be on the burner right here, right? And as you may or may not know, as you burn this fuel right here on the burner, the hot gases go up this flue in here, right? And they have this heat absorbing fins or a baffle that is inside there to slow down these products of combustion in this flue pipe. Right? And that's how I heat the water in that particular hot water tank. Is just this flue pipe goes straight down and brings the products of combustion out to a vent up here. And then the vent goes up and outside. So this is the vent up top. Okay? So for every 1 cubic foot of natural gas, we can calculate the flue gases. The flue gases are the ones that are inside the appliance. Okay? They're still inside the appliance. They have not reached the vent as of yet. And these are called flue gases. So what we do is we have 1 cubic foot of fuel that is burned. So if I have CH4 and I burn 1 cubic foot, and then we have to add our total combustion air to that. And we know through our math in the previous little bit before our break, we know that for every 1 cubic foot, I need 10 cubic feet of theoretical air and 4 cubic feet of excess air. So I need 14 cubic feet of total combustion air for 1 cubic foot of natural gas, correct? So I actually add these two things together to get my flue gas total. And my flue gas total is 15 cubic feet. So I add the amount of fuel that's burned and I add my total combustion air to get my flue gas total. And now, because this appliance has what is called a draft hood, this is a draft hood. And at this point, it allows air and cooler air to enter in this draft hood. And we call this air that enters dilution air. And this dilution air enters the draft hood at the bottom, and what it does is it cools down the products of combustion. Right? If we're allowed that very hot gases to flow through that vent, it would condense too quickly. So we're trying to cool it down. So at this point in the flue, we have 15 cubic feet of flue gases in the flue right now. Dilution air is 100% of flue gases. So if I have 15 cubic feet of flue gases per hour, I will have 15 cubic feet of dilution air per hour going into my draft hood. And then that would give me my vent gases. And my vent gases are dilution plus flue. So my vent gases are 30 cubic feet. And that's 30 cubic feet of gases rising up through the vent every hour. Or, excuse me, for every 1 cubic foot of natural gas burned. So this is some of, like, we'll go over this again at some point. What I'm trying to do is just get you to the understanding of how much air is required to burn hydrocarbons. And I guess that's one of the reasons why they want us to stop burning hydrocarbons, because look at how much gases are being put into the atmosphere from just one appliance. And these gases in here will be carbon dioxide, it will be water vapor, it'll be also maybe some small particles of carbon monoxide. We try to keep those out. Okay, try to keep those out all the time. But it's mostly carbon dioxide and water vapor. Right? And that is the bad gas, apparently, according to Al Gore and everybody else on the planet. And that's gases there. Now, for the next portion of this class, I want you to grab your gas code book. Oh, keeps on going to a circle. Gas code. Okay. Grab your gas code book. And I'll give you a second to do that. So I'm sure everybody's kind of got their code books there, kind of sitting in front of you. So this exercise, so to speak, is just to see a little bit about your code book. Everybody see my code book on the screen there?
Yep.
Okay, perfect. So this is the digital copy, and I think one of the students posted that. I don't know who, and I'm not going to name names, but there we go. You have a digital copy of this code book. Now, as you can see, we have in this code book, there's a little bit of, let me say, vernacular on the top. Let me just get it a little bit smaller. There we go. And if we go through these pages, right on the contents here, we have the scope of what this code book is about. And that is in section 1 is the scope. 2, we have publications, reference publications. 3, definitions. And then 4, and this is the part of the code book is 4 is general. And general covers a lot of rules around gas and around the equipment, even training, labor, responsibilities of the installer. And we're going to get into that minutia, so to speak, of this gas code in future classes. Section 5, pressure controls. So this is mostly about regulators and relief devices on pressure controls dealing with gases. Now these are natural gas and propane gas. Okay, this is what this is about. Section 6 is all about piping, tubing systems, gas hoses, and fittings. And we need to understand a bunch of that stuff as well as we move through the gas code book. Number 7, or section 7, I should say, is all about installation of specific appliances. If you have an appliance and you're not sure about some of the rules about installing any particular appliance, you look in here and you will find the rules associated. And now these rules, you're going to see a lot of words like should. Okay? Let me tell you one thing. When it says should, it means you have to do it. Okay? This is a legal binding document. And these are the rules in which we abide by in this province. Now, I'm not going to talk about what happens on Grandpa's farm in Saskatchewan and what he does with his gas lines and how he makes stuff, because a lot of times they don't follow the rules around this stuff. So that may be outside of the rules, and then when inspectors show up, people freak out because there's all kinds of rules being broken. So we're not going to talk too much about that. As the rules come down to it, Alberta Municipal Affairs is the authority having jurisdiction, meaning they tell us if it's going to be good or not. And then that authority having jurisdiction drops down to the municipalities. And then the municipalities then interpret the code as they see fit that apply to their certain areas. Sometimes you get a safety codes officer or a inspectors, plumbing gas inspectors. One says something different from one to the other across the city. Okay, it comes down to the interpretation of the code and how they see it. Now, they're both right. Okay, they're both not wrong. They're both correct if there's a little bit of disparaging from one inspector to the other. That is okay, because what we do as plumbers and gas fitters to the authority having jurisdiction, we say, yes, sir, thank you, sir, no more, sir, right? If you want me to do it this way, I will do it this way. If you want to actually talk to an inspector before you call them to inspect your job, guess what? You could call 311 and ask to talk to an inspector. You could talk to a live person. In this municipality, you are able to do that. Okay? And then they could walk you through it. My neighbor, who also lives in MacEwan, is a plumbing inspector. And he is my direct neighbor. He lives right beside me. He does all of his inspections in a virtual environment. He gets people to download an app on their phone, and then they walk through the building with their phone while they're recording that particular plumbing or whatever it is that they need to be inspected, and then he will approve or disapprove it via this app. That's how the new world is working. Bigger job sites, of course, they come on site. And then they have to do all the protocols of social distancing and masks and everything else. But for the most part, most of his day is sitting in his vehicle watching videos of people's houses, approving or disapproving of it. So again, they are the authority having jurisdiction. You're going to say yes, sir, no, sir. You start arguing with the safety codes officer, and then you're going to be... It's tough to go back from that, okay? Because every time they show up and they see you, they're going to go, oh, this effing guy. All right, I'll show you. We'll give you red tags for anything, all right? You want to build the relationship. These guys are plumbers, gas fitters, just like you, right? They understand what you're going through. They understand what you got going on. Communication, communication, communication. Matt, thank you for that. What if an inspector is wrong? Well, again, you should have your tools ready at the arm, meaning your code book. You should have it ready, and you should try and communicate appropriately with the safety codes officer to say, my code says this, how do you want me to do it? Okay? He is like your client. You want to please him, so to speak. Okay? It's like your boss. You want to please him, so to speak. Okay? So there's always ways to approach things, right? I mean, we're not selling refrigerators to Eskimos, but we need to get along because it's a small swimming pool, right? And we don't want to be, we don't want to be drowning anybody. Any other questions? Okay. I do get on my little soapbox every once in a while, don't I? All right. Section 7 is all about installation of specific types of appliances. Section 8, venting systems and air supply for appliances. And we're going to spend some time in this one for air supply and venting. And we have to determine air supply for all of our appliances, openings, etc., etc., etc. And it goes on and on. There's a little bit to it. So that's okay. But this is where we're going to find all of our answers for venting systems and air supply. Section 9. Whoop, I went too fast. Section 9, natural gas compressors and cylinders. So we don't do a lot of natural gas liquid, but we do have compressors on some ends. And then we get a little bit more on vehicle refueling in section 10. And then we have annexes. This gives us a bunch of different information around stuff. And then it lists all of the tables that we will use for our gas theory. And then it gives us figures of vent passing through roofs. And that is about it for that. And then we get into the people who put this thing together. But I do want to show you something before I go too far. And this is at the back of the code book. So I'm going to scroll. Wow, I'm going to scroll a long ways. Oh, where am I here? Scrolling. Oh my gosh, it's never ending now. Sorry. Welcome to your seizure. Okay. Turn to page 255, please. You get to page 255, and there's a properties of propane, butane, and natural gas. So I just want to chemical formulas. Look at propane, butane, natural gas. Molecular weight. Okay, not too important. Freezing point at atmospheric pressure. And this is a gas. They're talking about a gas. 260, 269. Boiling point. Boiling point clearly means a liquid. Yes, boiling point clearly means a liquid. Normal state at 60 degrees Fahrenheit. That is at standard temperature. And then they also put at atmospheric pressure. And at that point, they're all gases at that point. Relative density as a gas. They have propane at 1.52, but we use a 1.5 as a loose affiliation. Butane is 2. Natural gas at 0.55, but we usually use the 0.6 for natural gas right here, okay? That is one thing that we do. And then this 1.52, we usually just make it 1.5. Okay, so that's where a little disparage a little difference there. Relative density as a liquid. Propane, as you can see, propane is 0.51, butane, natural gas. Mass per gallon. Okay. 5.1 pounds per gallon. Okay, under propane, right here, it tells you it's 5.1 pounds per imperial gallon. What's so funny?
Oh, nothing.
I don't know. We'll see.
Nothing that you're talking about. I'm sorry.
Okay, excellent. I'm glad. Okay, calorific value in BTUs per cubic foot. We use the loose affiliation of 2,500 in this point right here. Okay, so when I say 2,500, that's what that is. The calorific value for butane, I use 3,200 right here. Okay, so just so you know, there's just a little bit of variance there. And then natural gas, 1,000 BTUs per cubic foot, and that is calorific values.
Does it make a big difference with that little amount?
We will use these numbers, Brittany, 2,500 and 3,200, okay? We'll use those numbers. Okay, so it's not a big difference. I mean, we're talking about 20 BTUs. I mean, give Grandpa a turkey sandwich for lunch, and he's going to be producing 20 BTUs before you know it. What, is that not true? I mean, it's true for, anyways.
And my grandpa's dead, so.
Oh, well.
Feel that.
Wow, suck the joy right out of the room there. It's just horrible.
Figured you were just talking from experience.
Well, yeah, my wife says as much, right? I just tell her to breathe deeper; it goes away quicker. That's all. That's.
And sorry, I just missed the part of it. That relative density of natural gas was 0.5. Or...
No. Natural gas right here. Oh, as a
gas, sorry.
Yeah, 0.6. We're going to use the number 0.6 right there.
Okay.
Okay, it has 0.55, but we'll use 0.6.
Okay, thank you.
Thank you for keeping us on track there, Josh.
No problem.
Things can get sideways pretty quick, eh? Okay, we're going to talk a little bit more about this. So this is vaporized, meaning from a liquid to a vapor. And this number right here is BTUs. And this is the one we want to be concerned about, is propane liquid. And that's how many BTUs I get out of 1 gallon of propane liquid. I can get 109,956 BTUs out of it. We'll talk more about that too. But that's the important number. Now, we also have cubic feet of vapor from 1 pound. I can get 8.5 cubic feet of vapor from 1 pound of liquid. And we're only going to be concerned about propane for this one. Similarly, cubic feet of vapor for 1 gallon of liquid at 60. 1 gallon, I get 44 cubic feet of vapor for 1 gallon of liquid. And this is imperial gallons, by the way. Okay, this is not US gallons. This is imperial gallons. Latent heat of vaporization, meaning you get 185 BTUs per pound of propane, and that's the one we're going to be concerned about as well. Latent heat of vaporization, specific heat, mass, density. Okay. So as you can see, there is some things, and now you have all of that information right in your code book. Okay? All that stuff we wrote down is right here. And it continues with metric equivalence. The next page is all metric equivalence of those numbers, is the next page.